So hi everyone, I'm Tomer. We will meet here. Welcome to the first recitation of AG Code. We will meet here every week for 1 hour to see some examples or exercises to have a better understanding. Um, so the recitations are recorded and they will be in English. But please do attend and feel free to ask questions and tell me if it's slow, too fast. The goal of today is just to uh, have a quick refresher on abstract algebra, rings, ideals, some of the things that Gil mentioned in the end of the lecture today. So maybe some of you already know it, that's okay. Just to make us feel comfortable with these things. Okay, if you want to discuss some things about the course, feel free to email me or approach me at the end of the recitation. I will be here for, I'm available after it, so we can talk. And any question? Great. So let's begin. We'll begin with some definitions, recall the definitions, and then our goal is to prove the bijection correspondence between points and maximal ideals in 1 or 2 dimensions. Maybe we will need some of the other. We will finish only next week. So let's see. So how many of you are familiar with rings and ideals? And okay, so almost anyone. Okay, so I will let's do it quickly. So what is a ring? Uh, so our rings will always be commutative with identity. So it set R with 2 operations, the addition and multiplication, into spatial element 0 and 1, such that R with the addition then abelian group, and R with the 0 is the neutral element, and R with the multiplication is a abelian monoid. So almost a group, but not not all the elements are units, not invertible, right? And where the multiplication is distributive over the addition, so get this. This holds for every A, B, and C the range. So some examples of things that we like. Maybe you can suggest. Right, the integers, any field K, polynomials, and variable x1 to xn over ring R. And much more. And again, all the rings that we will talk about are commutative with 1, unless we'll say otherwise. Okay. And so what is an ideal? An ideal is a subgroup such that what?
subgroup is normal, and it like eats multiplication of both sides.
Right.
Like you take an element from the ideal, and then if you multiply it by any polynomial or any, ring element
Exactly.
from
For
both
every
sides.
ring element and an element from the ideal, we have if we multiply the element from the ideal with the ring element, we stay in the ideal. So example, in Z, right, so in general, NZ, the an ideal of Z. These are the subgroups, and you need to see that it's closed. If we multiply an integer with an element here, we stay there. And what if K is a field? What are its ideals?
There's no ideal, only the trivial one and
Right.
not the field.
So always we have the trivial, the zero, and the whole ring. And the field, okay, so once a non-trivial ideal must contain a non-unit, since once I has a unit, we can take its inverse, and we get that one is in the ideal, and then it must be the whole ring. So R times one is in I for all R. Okay, let's have another example. So let K be a field. So K always they will denote field, and take S a subset K to the N. So just a set of points in K to the N. Then the set of all the polynomials and variables which vanish on F, such that F is 0 for every point in F. So this set is also an ideal of which ring of this polynomial ring. So we can see that if we have F and G that vanishes on S, then their sum, the difference also vanishes. And if we take G times F, also vanish because everything is pointwise. Okay, and in fact, okay, so if S is empty, what is the ideal of the empty set? The entire ring. The other extreme is that S is everything. And then what is the ideal? On trivial, the zero. And in general, if we have S1, S2, and if S1 is contained in S2, then the ideal of S1 contains the ideal of S2, right? Of course, if F belongs to this, then it vanishes on all the points on S2, and then obviously it vanishes on the subset. So, right, and what is the minimal set that we can take here? A point. So what we will show today that, in fact, if K is algebraically closed, then the ideal of a single point is maximal. In fact, this is true for any field, but the opposite question, does every maximal ideal is a zero set of a point? This is only if K is algebraically closed. Okay. So, few more definitions. Okay. let's define prime and maximal ideals. So these are always the proper ideals. So the proper means it's not the whole ring. A proper ideal I in R, which is not all R, proper, is prime if what? If for every A and B in the ring, if AB belongs to I, then A is in I or B is in I. Okay, and it is maximal if it's maximal with respect to inclusion. So if uh, there is no uh, proper J such that J strictly contains I. That is not a R. So okay, so if an ideal is prime if whenever it contains a product, then one of the factors already must be inside it. And it's maximal if there is no proper ideal that strictly contains. So the two things that we need to remember about this one, actually Gil mentioned them today, is I is principal if it is generated by one element. If from R. So if it's of this form, then it is generated by A. Then such an ideal is called principal. And a ring is a PID, principal ideal domain, if every ideal is of this form. Can be generated by a single element. Okay? Two things that we need to know. P prime, you can only quotient is what?
Domain,
Right, principal. Integral domain, which is just a ring without zero divisor, with no zero divisors. And maximal if it is a zero. Okay, so these are super useful. Uh, and in fact, one thing that we can infer from this, since every field is in particular an integral domain, a field doesn't have zero divisors, every maximal ideal is prime. So we usually use the spec R to denote the set of all the prime ideals. And spec R is the set of all the prime ideals, and max spec is the set of all the maximal ideals. And where this contains in every maximal ideal is in particular. Okay, so questions so far? Okay.
can you say again what integral domain?
Yeah, a ring with no a commutative ring with without zero divisor. That means if a times b is zero, then either a zero or b zero. So like non-example is z mod 6z, since 2 times 3 is zero, but no one of them is zero.
Could it be clear that if an idea is prime, then quotient is given at the table?
So it's 2-3 lines to show it. Maybe if we have time. Sorry, but it's pretty much follows from the fact that if AB is zero, okay, so if it is prime, then we know that AB is in P implies that A is in P or B is in P. But when we go modulo P, this translates to AB is zero in the R. This implies that A or B is. So yeah. So so for example, the ideal generated by X in Rx. So all the polynomials that are multiples of X with real coefficients. So this principal ideal, is it maximal or prime, or so we can check the quotient, see that it is isomorphic to R, right? So one way to show it is to take the ring homomorphism that from here to here, from Rx to R, which substitutes 0 instead of X, then its kernel is exactly this idea. And the first isomorphism theorem says that we have this isomorphism. Since this is a field, this is maximum.
R is a field, question.
Yeah, R is the real number field.
Oh.
Yeah. And so let's generalize this. Suppose we have a point A1 to AN in A to the N. Then we can consider the ideal generated by not one, but all these functions. So an element in this ideal is of the form some multivariate polynomials times this plus some other multivariate polynomials times that times that. Yeah. So this ideal, if we consider the map from X had the x1 to xn to k, which simply maps each f to f at this point, substitute the point, so we get a value in k. Then this is a ring homomorphism called the substitution homomorphism, and this is exactly its kernel. So it's not trivial. We want to do some work to show it, but yeah, you can show that this is exactly the kernel of this map, and of course this map is surjective since every constant maps to itself. So again, what we get is that the quotient modulo, call it M, A, modulo MA is isomorphic to K. Again, a field, so MA is maximal. And so we can ask, okay, so is every maximal ideal of this form? So in general, no. Okay, so for example, in Rx, can you give me an example of a maximal ideal which is not of this form, not x minus alpha?
What? Can you?
Yeah. So we know that every ideal of the form x minus alpha, x minus a, in Rx, and the real numbers, polynomials over the reals in one variable. So these ideals are always maximal, because what we just said. But are there other maximal ideals which are not?
Well, like irreducible polynomial, but not.
Right. So great. So an example, x squared plus 1, then not linear, yet the quotient is isomorphic to 1. Right. So in fact, the substitution of homomorphism substitutes I, for example. And this is the kernel in Rx. So yeah, so when the field is not algebraically closed, there are more maximal ideas. Maybe. Yeah, because if it's not, yeah, because there is some polynomial which, if it's not algebraically closed, you can find a polynomial which doesn't have a root, and then, yeah, so we can find an irreducible polynomial without the root, and yeah. Okay, so as Gil said, we will, in general, to show that if K is algebraically closed, then every maximal ideal is of this form, requires some machinery from commutative algebra, the weak Hilbert-Nullstellensatz. I'm not going to use it. So instead, what we'll do is restrict only to the cases where n is one or two, and do it without using the Nullstellensatz. So let's begin. Okay, okay, some more definitions just for today. So let R be integral domain. So a ring with no zero divisor. And let A be a non-zero element. Then when do we say that A is a unit? If there exists B in R such that AB is 1. So, and the set of all units, we sometimes denote it like this. So for example, in the integer, the units are plus minus 1. A is prime. So now when an element in an integral domain is prime, if A is non-zero, it's not a unit, and for every B and C in R, if A divides BC, then A divides B or A divides B. So it looks familiar from the definition of prime ideal, and we will we're going to see that it's much related to the concept of prime ideal, and A is irreducible if again A is not a unit, and in C, if we can factor if A is the product of B and C, and when if it is irreducible, then if we can factor it, then one of them is a unit. Okay. And
can you define a unit just to educate me? Like the set R by X?
the set R by R.
Yes, this.
Yeah, the set of units.
So how do you define how do you define unit? Like everything that multiplies by X is the same?
A is a unit if there exists B such that AB is 1. So, and know that if R is a field, then the concept of prime and reducible element is non-irrelevant because everything is every non-zero element in a field is a unit. So this only makes sense if we are in a integral domain which are not. Okay. So we I don't know if I mentioned, I will upload the notes after the session, so you don't have to like. So in abstract algebra, you usually prove that again R an integral domain and A non-zero element, then A is prime, the ideal generated by A is prime, if and only if A is prime. And it's a nice exercise to walk the definitions 2 lines to show it. And if it is prime, then it's also irreducible. So this is one thing that we use. And moreover, if R is a PID, so for example, if K is a field, then Kx, the ring of all the polynomials in one variable over K, over a field, is a PID. Z is a PID, integer. Then we have equivalence. Then
how do you define a PID? Like
every ideal is principal. It's generated by one.
Every maximum ideal.
Every ideal.
Okay, every ideal is the.
Yeah. So PID, as for example, Z, Kx, Yk is a field, Yk is a field. Every ideal is generated by one element. Okay, so yeah, but not all the rings are PIDs. But when our ring is a PID, then we have a nice equivalence. A is prime. The following are equivalent. A is prime. A is prime. A is reducible. And A is maximum. So this holds in any ring. This holds any ring. This holds in a PID. Again, you can show it, simple exercise that show it from the definition, the fact that the ring is a PID, then irreducible is A is irreducible if and only if the ideal generated by A is maximal. And this one follows since if it's irreducible, then it's maximal, and then if it's maximal, then it's prime, and then it's prime, then A is prime. So anyway, the following is equivalent, so now we can easily solve the one-dimensional case. So from now on, let K be algebraic. So corollary, what is the spectrum of Kx? What are all the maximal ideals in Kx? So Kx is a PID. In fact, if you give me an ideal, how can I find its generator? A generator? I can just, okay, I need to prove it, but I can just take the polynomial of the minimal degree in this ideal, and then you can show that this is the generator. And okay, so I want A to be maximal. Okay. Okay. So every ideal is principal, so it's generated by some polynomial. I want this ideal to be maximal, so I need, since it's a PID, this polynomial should be irreducible. But if K is algebraically closed, the only reducible polynomials are which ones?
one.
Exactly. So
Just to make sure I'm not there. So algebraic close means like every polynomial has a like a
every
no.
non-constant polynomial has a root in the yeah. Okay. So this solves the case of the one-dimensional case, since we see that indeed every maximal ideal is of the form x minus a. What about, oh, sorry, the max spec. And what about the spec? So these are the maximal ideals, and now what are the prime ideals?
No?
Almost. One more. Okay, the zero. Because, okay, this is equivalent assuming A is non-zero. So when A is zero, okay, so yeah. So I would like to consider the zero ideal prime ideal because the quotient takes modulo the zero is kx and it's an integral domain. So for me, it's prime ideal. But obviously it's not. Okay. So now we can move on to the more interesting case of the plane. Well, and two. Okay, so our goal is to show that there is a bijection between the points in the plane and the max spec of the polynomial rings into variables. Again, case algebraically closed. And what is the correspondence? Then if we take the point AB, then it corresponds to the ideal generated by x minus a, y minus b. So we know, we already mentioned that this ideal is maximal. What remains to show is that every maximal ideal is of this form. So
What are that for?
Again, so we are trying to prove that there is a one-to-one correspondence between the points in K2 in the plane with coordinates where A and B are elements of K, and the max spec of Kxy, the polynomial rings in two variables. So given a point, I'll take the.
So the image is the max spec.
Yeah.
And left by.
Yeah. So given a point, I match it. I match it to this ideal of all the polynomial functions that vanish at this point. So this is in the max spec, and I want to show that every element in the max spec is of this form. There exist some points such that it is of this form. There are no other.
Okay, so you're assuming that K is the algebraic closure.
Yeah. Okay. So let's begin. So before that, one is a claim. And so let F be a. Okay, so now K is algebraically closed and F is some field, not necessarily algebraically closed, but so F is the general field and F bar is the algebraic closure. Like if this is R, this is C. Okay. So suppose we have a polynomial, a bivariate polynomial over some field F and non-constant. Then, so the curve defines the curve that it defines simply all the points in F bar times F bar such that F A B. So this is the curve, just the set of the points on the curve defined by the polynomial A. And the claim is that the is non-empty, and in fact it's infinite. So I'm not going to, maybe I only sketch the proof. So if you encounter this. Okay, so maybe we can just sketch the proof. So first, if F is a polynomial only in X, then what can we do? If it's a univariate polynomial, yeah, so we can take any value for B and A, which is the root of F. And since F bar is algebraically closed, we can always find the root. It's not constant. So, and of course, if you remember, algebraically closed field is infinite. So we have infinitely many options for B and only finitely many roots for F, for A. But anyway, we get an infinite set. And if it involves both X and Y, then we can write it as a polynomial in Y with coefficients which are polynomials in F. And then what can we do?
How do you define F bar?
It's the algebraic closure. F.
Okay.
So yeah.
So you assume that F is algebraic closed.
Right. This is some algebraic extension that is algebraically closed in Galois.
Yes, just assume that like before you assume that F is algebraic closed by itself, and now you assume like the closure.
K is algebraically closed and F is not. That's why I use F bar. Okay, so let's so if it contains both x and y, then we can write it as a polynomial in y with coefficients which are polynomials in x. And then what can we do?
Just plug any point to an and define some univariate polynomial in y and
Right.
some
Exactly. Let's consider the leading coefficient. We know that it is non-zero because the leading. Okay. So almost every value that we substitute here will get a non-zero, and then we get the polynomial in y which has a root. So again, we have infinitely many solutions. Is it clear? Okay. Okay. So now here's the kind that we will actually prove, and probably next time we will finish. So the claim is as follows: let y be a non-constant polynomial. Then here generated by A is not maximal. So we will have like two or three claims from which we can conclude the bijection that we want. So this is the first step. We want to show that if we have a principal ideal generated by some non-constant polynomial, then it cannot be maximal. So we need at least two generators. So we have such a. So let's consider the curve that it defines, the ZF. We know we just said that ZF is non-empty. So let's there exists AB at power squared such that FAB is 0. Okay. So we can consider the following ideal: x minus a, y minus b, which is an ideal of which ring? Right, F bar, xy. Because A and B are, maybe they are not in F, but they are in F bar, so ideal of this polynomial ring. But we want to work in this ring, so what can we do? We take the intersection of M bar with RB. So we take it down to our, and one can check that this defines a valid ideal in this ring. So it's not hard, just technical to make sure that it's indeed an ideal. And also, it's not the whole ring because so it's a proper ideal because one is not one is not does not belong here because one does not belong here. So okay. So now I claim that if FAB is 0, then F belongs to the kernel of the homomorphism that substitutes AB, right? If I take a polynomial in two variables and substitute A and B, and I get 0, then this means that the polynomial is in the kernel. And we already mentioned that this is the kernel as an ideal in F bar x1. Okay, so in other words, if F vanishes at the point AB, then it must belong to the ideal generated by these two. The ideal that fits here. From this it follows that F belongs to the ideal generated by F belongs to F. Sorry. Thank you.
Some of us can't see.
Oh, sorry. Thanks. Okay. So I claim that the ideal of F is contained in the ideal M. Why is that true? Well, F belongs to M bar, and F also belongs to Fx1. So F belongs to M, and it is true that if F belongs to M, then the ideal generated is also contained in M, and M is proper ideal of Fxy. So we are almost done, right? Because we want to show that F is not maximal, and here is some bigger ideal. So if F is not M, we are done. Because we found a larger ideal, a proper ideal that contains it. So what remains is to assume that F is M. Okay, so maybe I will keep the rest. So not just a few more lines, but maybe I will return to it next time. But just maybe just give some examples so we have maybe can illustrate better. So suppose, for example, that we take F to be this in Rxy, the reals. Just illustrate what we've done so far with the complete example and then finish next time. So suppose this is F, then in Rxy, then we just need to find the point AB, on which it is when we substitute it 0. So exactly, and it's in C squared. So the ideal M bar will be X minus I and Y. Okay. And M will be the intersection of this one with Rxy. So for example, X minus I belongs to M bar, but it doesn't belong to M. Okay, so I will stop here, and next time we will finish this and